Hi, everyone. We're very happy today that we have Professor Aisha Khalique from the National University of Sciences and Technology from Pakistan, who's going to tell us about computational tasks through non-universal quantum computation. Aisha?
Yeah.
Okay, please go ahead.
Okay, thank you very much. I'm very pleased to be here, and it's my first time in giving a talk at New York University, Abu Dhabi, and I hope that it would be of interest to many of you, and we can go ahead from here. So I'm going to talk about the quantum computation, a paradigm shift. So I chose a subtopic of it, that is doing computational tasks through non-universal quantum computation, which is my work. So I will start from a very brief introduction to classical computing, then what an entity of quantum computing is, which is a qubit, and then what quantum gates are, which do we use, a slight introduction to the known textbook quantum algorithm, and then what would you expect from a quantum computer, and then basically my work, and what are we planning to do next. So I start from a Turing machine. We know that a Turing machine is, so I'm assuming that I'll be starting from the very basics and then take you to the work that I'm doing. So a Turing machine is just a band which contains just the unary numbers and a blank space, and it has an algorithm, and it is assumed and it is proven that one can do any computational task that can be done through any algorithm. It can be done on this simple Turing machine. So this a table shows the algorithm to add two numbers, and you can give any length of the two numbers and it can add that on. So it's an adder, and you have the Turing machine at some initial state SA, and you choose from here which SA is it, from where it is starting, you know the starting point, and then it takes you through and it makes you takes you to this blank and then make it one and then move forward. This cursor has to move left and right and then add the numbers. There's another Turing machine, which is called the probabilistic Turing machine, which does an operation with some probability P. For example, it will change SA to SH bar and AH bar and move left or right with this D with probability P. Or it will do another thing, which means that ST bar, which is H is for head and T is for tail. So you toss a coin, and with probability 1 minus P, it will do the ST bar, AT bar, and move left or right. It's a probabilistic Turing machine. So both of them exist classically. The Church-Turing thesis says that the class of all functions computable by a Turing machine is equivalent to the class of all functions computable by means of any algorithm, which means that if you have an algorithm, it should be solvable on a Turing machine. There is no such algorithm that cannot be solved on the Turing machine. The strong Church-Turing thesis, on the other hand, says that a probabilistic Turing machine can simulate any model of computation with at most a polynomial increase in the number of elementary operations required, which means that if you do a computation and you increase your size of the problem, then the number of operations that you require to solve that problem will increase in a polynomial time with a number of elementary operations. So the quantum computation, in fact, does not violate the Church-Turing thesis. So any algorithm that cannot be solved classically on a Turing machine cannot be solved on a quantum computer as well. But it does violate the strong Church-Turing thesis, which means that there can be a probabilistic Turing machine which can simulate some operations in a polynomial time, which a classical Turing machine cannot, classical probabilistic Turing machine cannot do, right? So we move ahead, but what sort of problems do we expect? So there are certain complexity classes. We have a P space, which is this inner space P. And in this P space, there are other problems which can be solved in a polynomial time, and they can be checked in a polynomial time as well. But there are certain problems which are NP, which are called the non-deterministic polynomial time problems, which can be solved on a non-deterministic Turing machine. With the polynomial can be done in the polynomial time. They can in fact cannot be solved in the polynomial time, but they can be checked in the polynomial time. So, and there are NP-complete problems. There are certain NP-hard problems which are as hard as any other problem, and which are both NP and NP. They can NP-hard. They are in fact in the NP-complete problems. So, what sort of problems are those? For example, the which I can tell. For example, the P problem. They are the testing if a number is prime. You can easily test that. Factoring, on the other hand, that if you know that a problem is you know a number, it's hard to factor it out into its prime factors, but it's easy to check that. So checking is in fact in the polynomial in the P class, and factoring it out is in fact in the NP class. So let's leave the rest. But so in it, what do I mean by the polynomial time and the polynomial resources? For example, a traveling salesman problem in which there are these 5 nodes in which one has to go, and it's a Hamiltonian cycle, which means that the walker has to visit each port at least once, or exactly once. And if you use brute force, then the order of operations that are required are n factorial. N is the number of ports that can be there, which is 5 in this case. And if we use a dynamic approach, that at each spot we change our decisions, and it would be the operations required would be n squared 2 raised to the power n. So this 2 raised to the power n is actually an exponential number of operations that are required. N squared is in fact polynomial, but it is classically an NP hard problem. So what can quantum mechanics do? Quantum computation do? There are certain problems which are in this NP class. We can, if you allow certain error in it, which quantum computation does do, it has certain error in it, and if you do it, we call it bounded error quantum probabilistic polynomial time. So these are the BQP problems, and these can be efficiently solved by quantum computer. So there is no exact boundary neither for P, nor for NP, nor for NP hard, nor for BQP. So we don't exactly know what sort of problems will be solvable on this. We just know certain class of problems that are not solvable in the polynomial time on the classical one, and we can solve them on the quantum computer. So let's look at what's different in one of such as we know is the RSA encryption scheme, one that is used there, which is based on the prime factorization. For example, in RSA encryption, where we can test the NP problems and the difference between the NP and the BQP problems. There is a public, it's based on the public and the private key. So we have 2 keys. So it's just like that you have a public key by which you can encrypt the data, and then you have a private key by which you can decrypt the data. So the private key is made by a number D, which is a prime factor of an NP. So number D is known to everybody, and then it is difficult to prime factorize n cross P. So into n cross P. So somebody who does know only D cannot easily prime factorize into n into P. So the classical complexity, that is how hard it is to prime factor a number, it goes as order of under root n and log of under root n log n, and it's very hard. But for the Shor's algorithm, its order is only n cubed, where n is the length of the number, or the in the binary digit. So it would be it's very hard, in fact, to do it classically, and it's easy to do it in Shor's algorithm. So this is what how you see that where BQP comes in. This is one of the algorithms. So there are some known algorithms where the BQP works, and NP for some NP problems. So what's so different about the classical and the quantum computation? One thing is the qubit. Qubit is the basic entity of the computation, just like a bit. A classical bit has just 2 values, which is 0 or 1. While a quantum bit can exist in the superposition. In fact, it can exist as alpha 0 plus beta 1. It can be 0 plus 1 over under root 2. So it's not only just this top point and the bottom point. It can be superposition of the two. It can be 0 plus 1 over under root 2. It can be the other way direction, 0 minus 1 over under root 2. It can be 0. It can be any other point on this block sphere. So we consider a block sphere, which is just like a sphere. And any point on the surface of the sphere is like a state of a qubit. And since there are infinitely many points on the surface of the Bloch sphere, so it means that there are infinitely many possible states for a qubit. So a qubit can exist in infinitely many possible states. So psi is alpha 0 plus beta 1, where alpha and beta can take any values. Those are complex numbers, with just a condition that alpha modulus square plus beta modulus square should be equal to 1. So with these infinitely many values, it means that a qubit has more power than the classical one. And a qubit can be any entity that can take two states. And in fact, it is a linear superposition of the two states. For example, it can be a Schrodinger cat, which can be dead or alive. It can be a polarization of photons, horizontal or vertical, this one, or it can be spin of an electron, horizontal, up or down, or any other quantum entity, the energy levels of an atom, which can take two values. It can act as a qubit. With an additional power than the classical bit, that it can take infinitely many states as infinitely many superpositions of 0 and 1. So what happens then in the computation, that if we have a single qubit, then we have our state as psi is equal to alpha 0 plus beta 1, as I said earlier, where alpha and beta are fixed by where on the Bloch sphere it lies. And if you have a 3 qubit state, then so we have 3 of them: alpha 0 plus beta, alpha naught plus beta 0 plus beta naught 1 into tensor alpha 1 0 plus beta 1 1, tensor alpha 2 0 plus beta, and so on. And then if we just multiply them, so we have 8 terms like that. So we have 8 possible combinations of 3 qubits. So we have alpha 0 plus beta 1 tensor 2 of other such terms. So we have alpha naught 0 0 0, alpha 1 0 0 1, 0 1 0, 0 1 1, and all the linear possible solution combinations. So just like a single qubit, there are infinitely many possible combinations of these, with these alpha naught, alpha 1, alpha 2, alpha 3, and all of them fixed, with only one condition, that their modulus square should be equal, sum of the modulus square should be equal to 1. So if I do an operation on this state now, for this state psi, which is of 3 qubit state, I'll be doing an operation on all of these 8 states together, right? So rather than doing one single state on a classical combination of 3 qubits, 3 bits, I'm doing an operation on all these 8 states simultaneously. 2 raised to the power 3 they are. So if there are n, there will be 2 raised to the power n state vectors. And there will be a linear combination of all of them, alpha x, and x is each entity, such that x is 0 0 0 or 0 0 1 here in the above example. So if I have, for example, 1,000 1,000 of them, then 1,000 qubits, then for each operation that I do, nature would keep track of 2 raised to the power 1,000 complex alpha x, because in each operation, these alpha x change their values, because each quantum operation takes a qubit from one point on the Bloch sphere to the other point. So these alpha changes. So it keeps track of all of these alpha. But now, how do I know what the state is? So I have to measure it. But when I measure it, in quantum mechanics, it collapses into one of the states. So psi, when I measure it, it will collapse into 0 or in 1, with probability alpha modulus square into 0 and probability beta modulus square into 1. Which means that if I measure one of the x here in this example, then it will collapse into one of the states of all these 8 or all these 2 raised to the power n, with probability alpha x modulus square. So in this case, it would be, in the end, we will be getting only one answer, just like a classical one. So what's the advantage? How do we gain from this qubit state? Even if it contains infinite information, we are gaining in the end. At the end, we have to make a measurement. And when we make a measurement, we just gain one information about the one state. And that was the case with the classical one as well. So what's the advantage? So what we do, so as I said before, the quantum gates are there when we do any operation on these qubits. We, in fact, do unitary operations. So we can think of any unitary operation, taking a qubit from alpha 0 to beta 1 to new values, alpha prime, beta prime, at new point on the Bloch sphere. So it's a sphere on the surface of which the tip of the state lies. And this point gives the state to it. And it gives the new values to alpha prime, beta prime. So it just moves the point to another point. And these are the probability amplitudes, alpha prime and beta prime. In fact, these probability amplitudes, they can add up destructively or constructively, right? So we can manipulate paths to cancel wrong answers destructively and reinforce correct answers constructively, right? So this is what we do. That we write our algorithm in such a way that we make these probability amplitudes to cancel each other for the wrong answers and to reinforce each other to add up constructively for the right answers. So this is what the whole quantum algorithm does. So in fact, for an algorithm, the quantum operation is done in the beginning, and the rest of the circuit is to read that answer in the end, or to make those wrong answers disappear. Okay, so this is what the quantum algorithm is good at. These probability amplitudes are not there for the classical ones. So the classical one is a particular state, alpha 0 plus beta, is a state 0 or 1. So it doesn't contain these alpha and beta, which can add up constructively or destructively, right? So this is what the power of quantum computation lies. There are some quantum gates, what they can do. For example, there is an X gate. As I said, that these gates are these unitary operations which can move a point on the block sphere to another point, and it can. So what can it do? The first thing is that here is that an X gate. So X gate, it flips the 0 to 1, and as I said, it's alpha 0 plus beta 1. So it can make it beta 0 plus alpha 1. So it can flip a qubit, right? So it's a NOT gate. It makes a 0 1 and a 1 0. And so keep in mind that the original state is alpha 0 plus beta 1. So whenever we do a quantum operation, it acts linearly. So that is how the quantum operations are known to work. So it acts linearly on both 0 and 1, and it will convert it any state, alpha 0 plus beta 1. It can be 0, it can be 1, but it can be a linear combination. And the linear combination is converted into a new linear combination, which is beta 0 plus alpha 1. And a Z gate, what does it do? It it converts alpha 0 plus beta 1 to alpha 0 minus beta 1. It adds a phase to one qubit. So it does nothing to the 0, but it adds a phase to the 1. So this phase is missing in classical entities because these are not linear combinations. So this in between relative phase is not there in the classical gates. And then the Hadamard gate. The Hadamard gate, in fact, brings the 0 to the superposition of 0 and 1. So it will convert it to alpha 0 to alpha 0 plus beta 1 and 1 to alpha 0 minus beta 1. So it will convert it from a 0 state to a superposition of 0 and 1, and a 1 state to another superposition, which is orthogonal to that, right? So just to breeze through it, just to let you know how it works. So, and then the T gate, which puts a phase of pi by 4 to 1, and then control NOT gate is the one in which it's a 2-qubit gate. So if the state of the first qubit is 1, it will flip the second, otherwise it will leave it unchanged. And the swap gate, it swaps the states of the 2 qubits, and there can be many more. But let's see that what are the simple textbook algorithms that are known to work in this way. So we have a simple Deutsch algorithm. It is to check whether a given function is balanced or constant. So our quantum computer is, in fact, it can detect an answer. So it has an oracle, which can, so a function is, I can tell that a function is balanced if it has both 0 and 1. So the f1 is a balanced function. It has both 0 and 1. F2 is a balanced function. It has 1 and 0. F0 and F3 are constant functions, 0, 0, and 1, 1. And if I put my initial state as 0 and 1, and I have to check whether the function is balanced or constant, then I can put it through this circuit. I can apply a Hadamard gate on it first. So Hadamard gate on 0 gives it 0 plus 1. And Hadamard gate on on 1 makes it 0 minus 1, as I told earlier. So when it makes it 0 minus 1, there's a minus sign with it. And what does it do? That whenever we take so this oracle, this UF, it operates on both X and Y. And it takes a addition modulo 2 of Y and F of X. So if F of X is, and when it takes addition modulo 2, if Y is 1, with the minus sign in the y is pushed back, and it comes over here with the f of x sign. So if it's f of x is 0, it comes as +1. If it's 1, then it comes as -1. And when it's pushed back, my state, which was in with the x, was 0 + 1, because it was created in superposition with this h. So it was -1 f0 0 plus -1 f1 with 1. And then we apply Hadamard again, this Hadamard, in order to read our movement. So this is like enhancing the correct answer constructively. That is, we are taking it as it will be in the state 0 with this coefficient. And if f0 and f1 are the same, then that is the function is constant. Then in this case, this term will be non-zero, and this you will measure 0, so you can tell that the function is constant. And if you measure 1, you know that they are different, and then this term will be this term would be in this case. So if they're same, this term would be 0. F0 and F1 are same, then this term would be 0, and the answer would be 0. And if they are different, then this term would be non-zero, and the answer would be 1. And you can immediately tell that whether the function is constant or not. So in the end of the day, when you measure it, you get either 0 or 1. But from that measurement, you can tell whether the function is constant or is it balanced, right? So this is a simple algorithm which works every time, which works with 100% efficiency. And in order to do classical, for example, do it classically, you need to know 2 number of bits in order to do that. For example, if you have to tell that the function is balanced, you need to know the value of first bit as well as of the second bit. You cannot tell by just knowing that the first bit is 0, because if it is 0, it can be 0 0 or it can be 0 1. So you have to know 2 bits. But with quantum mechanically, you only need to make a measurement in the end on this 1 qubit, and by making a single measurement on 1 qubit, you can tell the answer. So your efficiency has increased. You have used lesser number of qubits in order to find the answer for the same. So it's a simple explanation for a simple algorithm for quantum computation. So what do we expect from a quantum computer to do? Of course, we have some algorithms, but if we need a quantum computer, what do we expect? We need it to be measurable, right? As I said before, that at the end of the day, we have to measure the qubit in order to know its state and, in fact, read the answer. So it has to be measurable in the end. Then it should be universal, which means that it should be able to solve all possible problems that are addressed to it. If it can solve one sort of a problem, it can solve all problems that can be solved, that can be given to it. And it should be scalable, which means that if you increase the size of the problem, then it should be able to handle it, right? So it should increase the resources that you need, number of qubits or number of gates that you need to perform it. They should not go exponentially high with the problem. And it should be initializable, which means that it should come back to its initial state so that it can be used for the new computation. So it should not be that we are exhausting our qubits at the end of each operation and we have to throw away the qubits, and in the end we are left with no qubits. So we cannot provide it with infinite supply of qubits. So whatever the process does, whatever quantum process does, it should bring it back to the initial state again. And there should be quantum error correction. So there is a big problem with decoherence. That is, whenever your qubits, they interact with the environment, they lose their state, right? So it means that they would, if it's 0, it can flip to 1, or so there should be some inbuilt process in a quantum computer which can do the quantum error correction. So you cannot work on it if it just does the if it cannot correct the errors that come into in their inbuilt. But the problem with the quantum error correction is that, like classical errors, classical bits, if they have an error, you can measure what the state is, and then you can correct the error. But if you measure a quantum state, as I said, that it collapses into 0 or 1, which means that you lose the state. It won't remain alpha 0 plus beta 1, but it will either become 0 or 1. So you have to correct the error without measuring the state. And you cannot also copy it. You cannot make a clone of it. So you cannot make a clone of an unknown quantum state. So these are the problems with the quantum error correction, that you have to do the error correction in such a way that you don't measure it and you don't copy it, and still you can correct the error in between while going through this process. So this means that there should be music in it: measurement, universal, scalable, and initializable and coherent. So if you want to read about it, how to build a quantum computer, it's a small book by Barry Sanders, from where I took this idea of music from there. So you can see it there, very short description of how you can actually build a quantum computer. So this is the DiVincenzo criteria, in fact, from 2000, which he said that if there is to be a quantum computer, it has to have these properties. Otherwise, you won't be able to call it a computer. So what we did was, in fact, we in my work and in most of the work that is being done, we just let go this universality. We say that, okay, we have certain class of problems that we can solve, and we just concentrate on that. So there are certain cloud computing which can solve optimization problems. There are certain problems that can be solved on a linear optical setup, and so we only look at those problems that can be done there. So here is the linear optical setup, which we use for our quantum computing task. A linear optical setup is what it is. It consists only of beam splitters and phase shifters, right? And then there are single photon detectors in the end. So in fact, any unitary can be given by a combination of beam splitters and phase shifters. So as I said, that any operation on a qubit can be regarded as a unitary operation. So you can, and since any unitary can be given by a combination of beam splitters and phase shifters, so we can use this optical quantum computing to solve problems. But the problem is that it can be only a finite setup, right? So we cannot have infinite number of beam splitters and phase shifters in order to accommodate all the problems. So a given linear optical setup will be able to solve only a set of problems that can be given to it. So if you go for bigger problems or problems that need more beam splitters and phase shifters, you cannot solve it on that. And in fact, there's another problem with it, that it is difficult to implement some non-linear operations on that. So we took this setup and we look at the quantum interferometry, and which is in fact this beam splitters, and then we try to solve the problem with it. So this is what we do. We looked at. So photon interferometry is in fact very known fact. So if we have in fact we have a beam splitter and we have an incident photon on it. So it has two paths. It can go to this detector, it can reflect and go to this detector, it can transmit, and it can go to this detector. But if you have two photons, so this red one and this green one, so it has, both of them have 4 possible options together. Both of them can go, one reflected and one transmitted, they can go to detector up, and no photon in this one. And the second option is both of them get reflected and they end up at one detector each, and they can both of them transmitted, and then again they will end up in one detector each, and they can both one reflect and one transmitted, and they can end up in this detector in here at the end. So but practically, so there are all these options should be possible. But if you have a 50-50 beam splitter, which means that it transmits and it reflects with equal probability, then for indistinguishable photons, which means that which do not have, in fact, we can, so indistinguishability means that we cannot distinguish which photon is which. Okay, we cannot track its path. So then in the end, we do not get these two middle possibilities. That is, there is a coincidence. Both the photons go to the same detector every time, which means that either both of them are in this detector or both of them are in the fourth case. So the coincidence is never observed. So the state is always 2-0 or 0-2. It would be this for indistinguishable photons. Why is this happening? In fact, this is happening because the photon down there is experiencing an additional, which is hitting the beam splitter from below. It is experiencing an additional phase, And in fact, we can these two destructively interfere, and then these two options do not happen. So we can utilize this feature that there are certain options that are cancelled out during this operation that in fact there's some destructive interference happening. We can utilize this to enhance this constructive interference to go to the right answers and cancel some wrong answers using this destructive interference. So, but for this, the photons have to be indistinguishable. So we introduce some distinguishability in photons, where there's sometimes, so we can see that how the time delay, how the distinguishability affects that. So if there are we can introduce the distinguishability using the time delay. That is, we just say that one photon arrives earlier and one photon arrives late. So there's some time delay in both of them. So if we have a photon and we can represent its profile by this Gaussian distribution, and there's a time delay in it. So we have to associate a frequency with that. So it is, this Gaussian distribution can be represented by, it has certain time delay and it has some variance, which is sigma. And if there's a time delay, there will be partially distinguishable. If there are time delay, you increase the time delay a lot, then there will be totally distinguishable. So we use this time delay as a scale in order to see how it goes. So if we have now these two photons, so we have the same case, and we have certain time delay in that. That is, we have added some distinguishability in that. Then we know that if we have this beam splitter action, we can give it as U11, any unitary, U11, U12, U21, U22. And for 50-50 beam splitter, of course, it will be like this. U is equal to 1, 1, 0, 2, 1, 1, 1 minus 1. But in fact, this beam splitter can be represented as a unitary operation. Okay, and as I said, that we are trying to simulate a unitary operation, so we are on the right track. So if I do this and I introduce a time delay, then I know that for this matrix U, I can define a feature of this U, which is called the permanent of U, which is U11, U22 plus U12, U21, right? Multiplying the diagonals and then adding them up. And there's a determinant of U, which we are all familiar with, that is having a minus sign in between. So these two characteristics of this coincidence probability of this unitary matrix U can be detected. And how? By using the coincidence probability. As I said, if my time delay is 0, there will be 0 coincidence probability for a 50-50 beam splitter. If the beam splitter is not 50-50, then in that case, it would give the permanent of U when the tau is 0. You can see that if the tau is 0, this term will go to 0, 1 minus 1. And if the tau is 0, this term will be 1 plus 1, 2. So it is 2 over 2 permanent of U. So I can get a permanent of U from a 50-50 beam splitter, from a beam splitter, for a 50-50 beam splitter, it will be simply 0. So for any beam splitter, for any unitary, I can get its permanent from this beam splitter. I can design this beam splitter in such a way that its elements represent my unitary, and then I can calculate its permanent by making this time delay 0. So at this tip, I'll be getting the permanent of U. And I can calculate the coincidence probability in otherwise that I can get the determinant. So in this case, I'm not getting the determinant, but since it's a unitary operation, and if it's a special unitary, its determinant would be 1. So let's look at this is known, right? So for two beam splitters, and we already know that. So what we did next was that there's a process called boson sampling. So it's as I said, that it's a restricted model of non-universal quantum computing. As I said, we can determine the permanent of U from there. And we can in fact find permanent of any matrix using this, and it would be given as with this formula, permanent of any, which you can sample it out in S1, S2, and SM, all of them, and you can find that. So it is just that it is easy to implement quantum mechanically using these beam splitters and phase shifters. You can find the permanent, and while it is difficult task to find the permanent of a matrix classically. It's an NP hard problem, in fact. So what we did was we look at the immanence of a matrix. So if you talk about the 2 cross 2 matrix, it has just permanent and determinant. but if matrix of a larger size, it has immanence as well. In fact, permanent and determinant are special kinds of immanence. For example, for a 3x3 matrix, if you divide it into classes, so I don't go into detail of that, but just the permanent, as I said, that you add up the diagonal elements and then you just multiply the diagonal elements and then just add them up. This is the permanent. You put a minus sign at alternate ones, it's a determinant. And we define certain classes which are defined as this, and it is determined by the character of the determinant, and you can find it from the from here that if it's 2 for identity and it's 2 0 1, so if you represent all of them by 2 0 and minus 1 over here, it will be an immanent for that. So what we did was, and there will be four possible permutations of that: 1 2 3, 1 3 2, 2 3 1, and 2 1 3, and so on. They are all alike. And what we did, we proposed a scheme that we can use time bin entangled photons, which means that our initial state is not just 3 or 4 photons, but they are entangled, and they are time bin entangled, and they are entangled in such a way that their coefficients are characterized by the character of the class they are in. Okay, so this is the character. For example, they are in the class. These are the characters for chi lambda. So if they are in this class, it will be 1 1 1. If they are in this class, it will be 1 minus 1 1 and 2 0 minus 1 and so on. So we took the initial state to be an entangled state, and then we send it through the beam splitter, right? It's a unitary, it's a beam splitter. It's a combination of beam splitters, which is a unitary. It can be, for example, if you are taking three photons, we can send it through any 4 or 5 of the beam splitter. In the end, we are measuring just the 2 or 3 of them, whatever the size of the unitary we want to take. And we can determine the immanence of from the coincidence count, we can get the functions of these immanence. So before that, we could only get, we could not separate out different immanence, but in our work, we have been able to, by taking the entangled state in the beginning, we can separate out immanence of different vectors. So what do we do with this computational task? We have an input, which is the number of input photons. We add the time delays between the photons in each input. That is, we make them distinguishable. Then there are partitions of lambda of n, right? So as I said, these are different classes. And there's a server which repeatedly injects time bin entangled multi-photon states and records the coincidences of detectors placed at each output port. And at the output port, we get, whenever it records the coincidence count. So from these coincidence count probability, which is this, it computes the functions of immanence, which is a function of only one immanent of the detector of the matrix, U matrix. So this is how we estimate the quadratic function. It is achieved of the sampling problem, and the quantum advantage that we have over the classical one is that it is difficult to simulate these experiments classically, and with these beam splitters and these beam splitter experiment, we can, which is a unitary operation of any size, and we can determine the size of the matrix. So the immanence of the matrix. What else we did with it? We looked at the biphoton interferometry, which is in fact interesting in integrated photonic circuits. And in this, we entered the biphotons into it, and we see how it works. So we have different coincidence probabilities, and we have looked at it. Of course, it just shows that where we expecting a dip, and where we can get different parameters of the U matrix from here. So this is one of the work. And then we moved on to another, non-universal quantum computing is by using the quantum annealer. So quantum annealing, as you know, that there can be different universal quantum computers. It can be topological, it can be adiabatic, measurement based, or it can be gate model. And there can be a quantum annealer, which can solve only optimization problems. So in a quantum annealer, each qubit is a superconducting flux qubit, which is QuID, and it is a 2-level quantum system. And it can solve, as I said, only optimization problems, right? So the problem we solved on that was a traffic optimization problem. So it was that at a junction, we have like these 6 routes in which your traffic can go, and at we control the traffic signals in such a way that there's a smooth flow of the traffic possible out there. Okay, So it is that how would, the question posed was this: how would one control traffic signals such that maximum traffic flow is achieved in minimum time? So without minimum, with minimum disruption. So for this, we need an objective function, of course, which relies on how much we have to, which relies on certain constraints. So using those constraints, we have to construct an objective function. I won't go into the detail. And so we have a speed limit of each connecting segment, and we input this to, and then we have a map of traffic signals. How does it go? And we have the current traffic density on each segment, and we construct a Q matrix from here, a Q matrix which is based on this objective function. In fact, it is XTQX, and from here we construct a Q matrix, and we send it to hybrid solver, which in fact solves it. This hybrid solver is a quantum classical solver, and then it keeps looping it keeps giving it the real-time traffic data, and it can give the traffic current density, and again it feeds into it, and then it interprets the result in terms of signal mode. So here where the D wave quantum computer comes into play. So we computed it. Of course, we do not get a classical advantage over classical, but if the number of qubits are more, then of course it can do better. But it does show that, in fact, it was proof of principle that it does work, and there's certain problems that can be solved on this optimization problems that can be solved on this traffic optimization. In fact, where we did get the advantage was this multi-commodity flow problem. So it was another graph problem in which we have multi-commodities flowing on that. So it is just submitted now. And there are multi-commodities which have to be transferred from one destination from one start point to the destination, and there are different routes with different capacities on it. And then we found it out that we can in fact do better. Sorry, I forgot to add that graph since it was very recent. So that there are certain time advantage over the classical one, so we can actually do it in a better way. And then another thing that we are interested in doing is in fact quantum internet, which also uses the quantum entities. And there's one way of doing it that a lot of work has been done on quantum cryptography, and the quantum internet is a related thing in such a way that you can build a connection between two entities using a connection between the two, so you can transmit a message from Alice to Bob. So we have just started doing this work, right? So we are not finished with it yet, but we anticipate that if there are multiple routes to connect two users, Alice and Bob, then there is a higher probability of succeeding, because it will succeed if one of the route works, even if others don't, right? So there will be a better probability of succeeding into that. So if we have, so it's an advantage over without entanglement thing, because if there are not only trusted nodes in between we have trusted nodes, then we can connect them. And even if one of them is faulty, all of them are faulty except one, it will work. So we are still working on that. So then another thing which is with entanglement is the quantum internet, and it is based on we use different quantum networks, and for example, a tree one and a lattice one, and we included noise in it and dephasing. And so at each step, whenever one goes from one step to the other, there's an entanglement connection between the two. And so an entanglement connection is established here, and then when it goes to this point, then an entanglement connection is established, and this connects these two, right? So in this way, in the end, the entanglement connection is established between the first and the last. So it works on the entanglement. So there is a package QuNET which we used, and for which we did different quantum internet with the entanglement. And if sorry, I'm just briefly going through these works so that if anybody is interested, we can talk about it more. And I've also worked a lot on QKD, and I've worked on long distance QKD modeling, and also key generation rates, how it can be done. So one thing that we have started now is, and it involved the modeling for the entanglement swapping and the discrete quantum key distribution. So we just started doing continuous variable MDI-QKD, and we are just about to submit this work. In this, we use the continuous variable measurement device independent QKD, in which you give your devices, measurement devices, to Charlie, and he does all the measurement, and you assume that Charlie can do anything. He just has to announce his measurement results. So in this way, any eavesdropper cannot enter into your offices and cannot gain anything from the result of your measurements, right? So in this way, you are sure that whatever they are doing, whatever the measurement they do on their part, and they just announce the result. So one thing we keep in mind that while doing QKD, we do not want Eve, in fact, does not want the communication to stop. She just wants that she should be able to listen to it. So she does not want to give the wrong answers to them. So she announces the measurement result, in fact, with the Charlie, and then from these measurement results, we find what the key generation rate is. So what we found in our work was this, that we can increase the key generation rate if we are in the low squeezing regime. So we have a scheme for increasing the measurement results for increasing the key generation rates for low squeezing regime, and we are normally interested in low squeezing regime because high squeezing is difficult to produce experimentally. So low squeezing is always easy, and if we can increase the key generation rate in that, which you can see, there's a considerable increase of distance, in fact. So so in this case, it's in fact a very advantage over the presently known schemes. Then we have also worked on continuous time quantum walks. In fact, this is also a distribution of information. So we have a quantum walk. A walker starts from here, and it goes from one side to the other. So it's just imagine that a walker is a qubit, and it goes from one side to the other. And qubit can exist. In fact, it can start in initial state into a superposition. So it can be, in fact, in a superposition state in the start, which can be in the beginning as a Gaussian overlap of all these states. And we have found that, in fact, if we start a walker in a particular Gaussian state, we can control its motion. So we can make it walk in a particular direction, and we can, in fact, suppress its walk in the other direction. So by just controlling the phases in between these two sides, and the Gaussian initial wave packet, we can control its motion, right? So this is how I connected with the bases, with the phases, and this is how it starts in the initial state. So it's a spread over all these vertices rather than on a single one, right? And then if it goes like this, it reaches here, and we suppress it from going down there, and it goes to 1. So here you can see it goes here, and it goes to this state with more probability. And then it moves until it reaches here at this point. And then we compel it to go here in this direction rather than coming down. And by just controlling the initial Gaussian wave packet and the phases in between. And although it is connected, right? So although this is connected, but the walker is suppressed to go in this direction. Not only that, but in fact, we can make the walker, which is connected to a path, and it will continue going in this direction. If it's a very, very long path, then we can make it turn back, in fact. And this we can do just by controlling the real part of this phase that we are assigning to it. So if you just change that, we can make the walker turn back. So this way we can gain information from the path and turn back and bring that information back. So we can, in fact, make the walker move in a particular direction and transfer and enable the transfer of information in a particular direction. So these are a few avenues that we are working on, and there are also a few more. We have, as I said, that we are working on trusted nodes. That is the work that is going on. We are working on modeling of quantum optics, some modeling in quantum optics, which is like how do we model detectors, like multi-mode detectors, and how we can use them in QKD quantum key distribution setups. So this is what which we are. So we are writing another work on quantum walks in open quantum systems, which was also a final year project for bachelor students. So we are going to submit that soon. And then there's a spectral analysis. And of course, we are using it for exploring immanent calculator again. In fact, right now we're calculating the functions of immanence. We want to scale it down to one immanent. And then modeling detectors, as I said, modeling QKD setups using that. And then even device independent QKD, more continuous variable quantum information, and in which we are also looking at the quantum internet using continuous variable quantum information. So these are a few avenues. So I hope that some of them would be of interest to you. So thank you very much for your attention, and I look forward to further discussion.
Thank you very much. Questions?
Hi, yeah. You mentioned this idea of quantum internet, maybe without entanglement. How would you be transmitting information across that network?
Okay, so here we have trusted nodes in between, right? So what we do with the entanglement, that we establish entanglement at each node, and then when the first and the last get connected, we transfer the information. So in this case, there's a trusted node in between which merges it and recreates it and then sends it to the next one. So at each node, so you just trust that whatever this node is getting, it is in fact sending the same state to the other one. Right, so this is just how the transfer of information is done in this case.
Right, sorry, I think I misunderstood. I thought that was meant to be without entanglement, but there's entanglement between each node?
No, there's no entanglement between each node. That I was saying that with entanglement you do it in that way, but without entanglement you have only the trusted nodes. You measure it and then resend it, right?
I see. So. But does that mean you're sending like qubits between nodes?
Yes, you send the information in terms of the qubits, but each person at the node, he measures it and then he creates a new state and then he resends it. So each, yeah. So the only thing is that you do it. So it can get lost in between, and it can. But if only one of the path works, then it will work.
Right. Oh, so my follow-up was going to be: is it realistic to have quantum internet where you have to send qubits between nodes instead of just bits?
Yeah, in fact, it is. It has to be measured at each node. So they have to, whatever information they do, in fact, they have to measure it. So in the end, they have to compute from each node. So if there's multi-path routing, then at least one of the paths would succeed to get the correct answer.
Right, thanks.
So when you talk about the quantum walks, you were labeling these numbers. Perhaps you could explain it, please.
These numbers?
Yeah, the number. Yes.
These are just the number of the nodes. So we are giving the walker a path. So these are just the number of nodes. So a walker can start from anywhere. We made the walkers to start from this. Its initial state was spread from 39 to 34 to 33 in a Gaussian manner. And it was a Gaussian initial packet centered at node 36. So it started from here. And then when it comes here, it has many paths to go. But by just selecting the initial state, we have make it move to this path only. Although this path is also connected, but it doesn't go in this direction. So by just taking the initial state and what the Gaussian spread is, we can make it go in one particular direction.
I see. So the labeling is directional in a way.
Yeah, the labeling is just for the number of nodes where it is going. So since we started from here, it goes to 1 after 31. It comes here after 30. It goes to this side.
Okay, very good. Thank you. Any other questions? Okay, if not, let's thank Aisha again for the very nice talk.
Thank you very much.
Thank you.